Edexcel Decision 1, Graphs and Networks 3, Planarity and Floyd's Algorithms, Hamiltonian Cycles. So first of all we need to recap two terms. The first term being path. A path is a sequence of edges such that the end vertex on one edge is the start of the next, and in which no vertex is visited more than once. So in this graph there are many paths, one example being B, A, E, C. Another one could be C, E, B, A, or D, E, C, and so on and so on. The second term we need to remember is a cycle. A cycle is a closed path, so that means you can only visit each vertex once, but we must return to the beginning. So for example, a cycle could be A, B, C, D, E, and back to A. And there are many cycles in this graph. So a Hamiltonian cycle is a cycle that passes through every vertex of a graph once and only once, and it must return to its start vertex. So in this graph, the obvious Hamiltonian cycle is A, B, C, D, E, A, and that's the one that goes all the way around the outside. There are other names for Hamiltonian cycles, and these appear on your screen now. And any graph that has a Hamiltonian cycle is also known as a Hamiltonian graph. Okay, so now for a brief bit of history on Hamiltonian paths and cycles. These are named after Sir William Rowan Hamilton, who invented a game in 1857 known as the Icosian game. This game involved finding Hamiltonian cycles in the edge graph of the dodecahedron. Now we can see below the dodecahedron, and we can see the edge graph, and then we can see the Hamiltonian cycle. Dodecahedron is one of 5 Platonic solids, and it turns out that Hamiltonian cycles can be found in the edge graph of all 5 of these solids. So does this graph have a Hamiltonian cycle? The answer is yes. So the first Hamiltonian cycle could be A, B, down to F, up to D, to G, E, C, and back to A. I could also do the cycle A, C, E, G, D, down to F, up to B, and back to A. But if you notice these two cycles, one is just the complete reverse of the other. So these cycles are in fact the same. So reverse cycles are not unique. I could have also started at a different starting point. For example, I could have started at B and gone B, F, D, G, E, C, A, B. And as you can see, that's pretty much in exactly the same order as the top cycle I wrote down, but just at a different starting point. So again, this is classed as the same cycle, and it is not unique. However, there is one other unique cycle in this graph, and that is if we went A, B, D, G, E, then up to F, down to C, and back to A. And this one is a second Hamiltonian cycle of this graph. So does this graph contain a Hamiltonian cycle? I think the obvious answer really is no. And that's because E is out on a limb. So we could start at E. If we started at E, we'd go to C, D, A, B, but the problem is we can't get back to E again. And every time we got to E, we'd get to a dead end. So it doesn't have a Hamiltonian cycle. However, this path here uses all the vertices, so it is known as a Hamiltonian path. Okay, so does K4 contain a Hamiltonian cycle? And if so, how many? So the obvious thing to do first is to remind ourselves what K4 looks like, so perhaps take the time to pause the video and draw it for yourself. Okay, so K4 is the complete graph with 4 vertices, and obviously every vertex is directly connected to every other vertex by the nature of the word complete. So, how many Hamiltonian cycles does it have, if at all? Well, obviously it does have Hamiltonian cycles, and the most obvious one is A, B, C, D, A. We can also do A, B, D, C, A. From A we could also go A, C, D, B, A, and A, C, B, D, A, and then we could also go down to D, C, B, A, and A, D up to B, C, A. Now we must look at these carefully to see whether they're all unique. So are there 6 Hamiltonian cycles or less? So if we look at A, B, C, D, A, B, C, D, A, that's actually A, D, C, B, A in reverse. So this one here and this one here are the same. One is just the reverse of the other. And then we've got A, B, D, C, A is the same. So these two are just the reverse of each other. And if you look closely, these two are clearly the reverse of each other as well. So yes, there are Hamiltonian cycles, and there are 3 unique cycles. We also know that if we started at a different starting point, it wouldn't give us a unique cycle, because the vertices would still be visited in the same order. In fact, all complete graphs have n minus 1 factorial over 2 unique Hamiltonian cycles. And it might be worth looking that up. Okay, so next session will be on the planarity algorithm.